Good morning, good day, everyone. My name is Khair Masood, and today I will be presenting you my paper, Mathematical Modeling for Performance Evaluation using Velocity Control for Semi-Autonomous Vehicles for 15th International Conference on Soft Computing Models in Industrial and Environmental Applications, SOCO 2020, which is being held in September 2020. So I'll just jump into the presentation right away. I'll first introduce myself, the university, and then I'll give a little bit summary about the paper, a little bit about the vehicle, and then the mathematical model we made and the velocity controller we made for it. And finally, I'll come to the simulation and results, and finally to the conclusion. So, about the university, we belong to University of Genoa, which was founded in 1481, and it's located in Liguria, Italy. It's a very big university consisting of more than 32,000 students and 2,500 staff members. It has schools, and within those schools, there's a polytechnic school which has a department, DME, which is our department, and within that department is our lab, which is PMAR lab. If you want to know more about us, visit our lab on the given web. So there are basically three authors. I'm doing my PhD from École Centrale di Nantes, France, and University of Genoa, Italy. I've got more than 15 publications and a lot of experience under my belt. And then there's my professor Matthias Zoppi, who has done his PhD in robotics. Finally, there's Luisa Mofino, who's also a full-time professor and is a renowned name in our industry. Now about the paper. This work is carried out for creating the platform where we can simulate our vehicle in order to judge our vehicle better. The vehicle is supposed to be performing autonomously in October 2021, so we are targeting that, and for that we need a lot of testing, and for that testing we need a testing bed or simulation bed. So this whole work is for that basic purpose, and we want to visualize our dynamics, and finally we want to have a platform where we can make our own controller. For that we have made our own velocity controller for this particular problem. And so what about our work? Well, in this work, we have basically made a mathematical model for judging the performance of the vehicle. That is required for embedding any new hardwares we wish to embed in our system. The mathematical model is pretty straightforward. It's right now it's on an empty straight road, and it assumes there's no inherent error are in it. The only varying factor from the environment is the elevation profile, which we got from the Google Maps. Uh, so about the vehicle. Well, the vehicle is a new concept, and it's a light duty, fully electric vehicle, and used is visioned to be used for efficient, sustainable freight transport in urban areas. It is one of the pioneering autonomous vehicles in freight delivery sector, and it is expected that it will be performing autonomously in European H2020 project show shared automation operating models for worldwide adoption. If you want to know more about the vehicle or the project show, you can visit these websites given below. This is how the vehicle looks in real life. It has two forklifts, and the cargo goes from the right hand side. There's a pilot which drives the vehicle, but it is a vision that the vehicle will be fully autonomous by the end of October 2021, and by the end of next year, hopefully. We are working on it, and this work is basically for that purpose. This is another diagram, a CAD diagram of the vehicle. And so coming to the mathematical model, our coordinate system is pretty straightforward. X-axis is along the nose, y-axis is from the left-hand side, and the z-axis is from the top. The constraints are pretty straightforward as well. The vehicle is unable to roll and move along the z-axis, of which the motion of the vehicle is along a straight line. There's no traffic or obstacles in the path of the vehicle. So vehicle is. So the mathematics, we have used four types of different forces which are acting on the vehicle. The traction force, which is basically generated by the engine. So that is the propulsive force for our vehicle. Then there's drag force. Then there's radial force, which is due to the gravity and slope of the road. And alpha in that denotes the slope of the road at that particular instant. Rolling resistance force, which is basically frictional force, is derived from the formula. In that, there are different formulae for calculating the coefficient of friction, and yeah, that's pretty much. So the longitudinal equation of motion is, and the lateral equation of motion and moment along the z in the format given below. But since there's no steering angle, so this component goes to zero. There's no velocity along y-axis, so because there's no deviation from the path, so this component also goes to zero. And since there's no inherent errors, so there's no moment, and so yaw angle also, yaw rate also goes to zero. When these all goes to zero, we our r is always zero. When r is zero, our terms in this and this goes to zero, and because there's no Vy, there's this force goes to zero, and there's no steering angle involved, so this portion also is. So there are two separate controllers for our cascade controller, because we have made cascade controller because the requirements for braking are different than the traction power control, because we might need sudden braking, but we will never need sudden acceleration, which can rev up the engine. So the best thing was to make a cascade controller when we are starting. So to simulation and results. So we used Google Maps and extracted elevation data from Google Maps. From the left-hand side, we took a profile in Genoa, with which the vehicle went, and we extracted the elevation profile, which is plotted on the. We tested over both of the controllers. The braking controller had a dead band of 1 km per hour. That is, the braking will not be initiated unless there's a error of at least 1 km per hour. So that's why you see these two peaks, which are more than 1 km per hour, because once the threshold is crossed, then only then is braking is applied. Because of the slope of the road, the vehicle velocity accelerates more than the road. So regarding the braking force, as I've mentioned, the right hand side is for right hand y-axis is for the velocity difference. The left hand side is the braking force. As you can see from this figure, the braking is only initiated when there is a difference of at least 1 km per hour, and as soon as the difference is dropped below 1 km per hour, the braking force is also diminished. That is, we have taken our foot off the brakes. So the mathematical models for work as per requirements. The velocity control remained within the desirable range of 2 km per hour. The vehicle was able to maintain its velocity over a hilly terrain, which was required, and future aspects of this are more required. This platform will be used for path planning, safe parking, cargo alignment, and enhancing the overall safety of the vehicle. We would like to thank the European Union Horizon Project Show, which I've mentioned earlier, the shared automation operating models for worldwide adoption. I hope this presentation you found this presentation interesting, and I hope if that you enjoyed it. If you have any questions, you have my email address at the start of this presentation. Feel free to contact me. Uh, Hope you like my work. Have a nice day and have a nice conference. Cheers.